There's always the first few seconds of every stream where I think like I could say some heinous shit and people will only see it in the video playback. They won't actually see it live and they won't react to it. And I was thinking like eventually we're gonna have to deal with the increasing population of the world, and like some kind of population control is gonna be necessary. And like, what's to stop that from getting eugenic? Like, shouldn't it be eugenic? Like, if you're gonna choose a certain percentage of the population that gets to survive and a certain percentage that doesn't, like, shouldn't you choose the more optimal percentage? I don't know, maybe that's kind of fucked up, but oops. All right. Hopefully people don't see the beginning of that stream. Where do I put this? There we go. There we go. Sure, that looks good. Yo, what's up, Predator? And Alex Guck. Oh, I recognize Alex. Alright, today I'm going to do number theory homework. What's up? It's really Zen. How's everyone doing? Man, recently I just been on the like feeling hella lazy, just like all I want to do is eat food and not not do anything else. Yeah, like it's just so much work to do math or like think about hard conceptual stuff. Like I just want to eat food all the time and like not really do anything else. And just like indulge in like simple pleasures of life. That's all I want to do. All this like trying hard at conceptual stuff for like long-term gains sucks. What about gym? No, dude, that's painful and bad. Like I just want to lie around eating food. Why is everyone in this community so damn disciplined? Why not like give up every once in a while? Why not forget about trying? Yeah, I mean, food is just like pretty banger. I was wondering about this recently. Imagine the textbook your prof bases their lectures on. Do you think any of their current previous students have worked through it cover to cover, like read it all? That's a really interesting question because like whenever I take a class, like there's a moment where I'm like, man, like I'm gonna be the best student ever to take this class ever. I'm gonna like read the entire textbook cover to cover. I'm gonna just be so insanely cracked at math. And like 2 weeks into the class, you're like, all right, I'll be happy with a C. I don't know. Maybe it's not that bad for you, but all right. Reading. Start reading chapter 4. All right, I guess I'll do that. It's kind of weird that it just says start. Probably be a much better like mathematician if I actually read my textbooks more. But reading math textbooks like requires so much effort because you have to like think about everything they say. It's not like a novel, and yeah. Why not simply work at the fulfillment center? Sometimes I consider it like I could just work at a grocery store, drop out of college, and like it would kind of suck, but at least it would be stable for like the rest of my life. You ever think about that? Like, what if I just like forget about all this the knowledge work and like just do something where I don't have to improve myself? Although I guess that would be harder in the long run. I've been reading Thomas Calc and just wondering, has anybody read the front page? Literally mentions arrogance in one's own ability, which is funny since many people won't read it for that reason. Oh, what's up, Poseidon? Yeah, I haven't seen you in a hot minute. um, yeah, yeah. Do math because it's fun. But I mean, can't you all relate sometimes? Like, I just want to like sleep and eat food, and not deal with all this thinking. Oh, goddamn real analysis. Um, Wait how bad your mental state will be once you finish it. Um, yeah, yeah, it's absolutely ass. Well, um, also I've just been like absolutely. I've been on my. I don't like when people say I've been on my. It's like not correct. Recently, I've been just going to class and like zoning out the entire time. I don't know what's going on with my schedule of thoughts or whatnot, or yeah, you ever just show up and like not pay attention at all? I've been doing that a lot recently. Not really enjoying it though. It would be good if I could pay attention. My thoughts have been wandery AF. All right, where's the textbook at? It said start reading chapter 4, and then we've got problems 2.4. I'm gonna drop a fat bookmark. MP. Is that how you do a mark? Yes. Okay. Chapter 4. That's chapter 3. Primes and their distribution. And then we got chapter 4. Theory of congruences. You guys want me to make this like a single page view like this? Or do you prefer multi-page? All right. I know it's better to spend more time on proofs than reading because I did it the other way around and I thought I was retarded because I couldn't prove trivial theorems. Yep. Black Pen, Red Pen has good videos on the definitions, applications, the limit definition if you're a little unfamiliar with them. Okay, thank you. I'll check that out. Probably you have not covered prior material, which makes the class boring, but also sometimes you're just in the mood for it and your body just absentmindedly drags itself to class. That's great advice, yeah. Honestly, I should do that more, like just I have to stay more on top of the reading for classes. Like math class is not as bad, but like I'm taking the Gen Ed linguistics class, and that I like just cannot pay attention to it to save my life for some reason. I still pay attention to it because you can get jump scared, or I still go to class. You can get jump scared if you don't go to class. How do you stop your hair from getting oily like shampoo? Why do people always ask me hair questions? I don't know. I have no idea. All right. Reading chapter 4. This is the type of reaction content we get around here. Gauss once said mathematics is the queen of the sciences and number theory is the queen of mathematics. If this is true, we may add that disquisites, disquinosities is the Magna Carta of number theory. Okay, cool. Not sure that added much to my my understanding. Cool. Cantor. But so basically, number theory is the queen of math, and math is the queen of science, so it's double queen. All right, another approach to divisibility questions is through the arithmetic of remainders, or the theory of congruences as it is now commonly known. The concept and the notation makes it such a powerful tool. That makes it such a powerful tool was first introduced by the German mathematician Carl Friedrich Gauss. I'm not going to try to pronounce that again. Disquisitions, Arithmeticae. The monumental work which appeared in 18... Okay, I'm not exactly sure how important this history of math is. It's kind of cool, but I'm trying to get onto the math. Here's the man himself. Oh, he was an infant prodigy. Okay, this is getting interesting. Natural aptitude for mathematics soon became apparent. As a child of age 3, according to a well-authenticated story, he corrected an error in his father's payroll calculations. His arithmetic powers so overwhelmed his schoolmates that by the time Gauss was 7 years old, they admitted there was nothing more they could teach the boy. It is said that in his first arithmetic class, Gauss astonished his teacher by instantly solving what was intended to be a busy work problem. Find the sum proof that school is busy work. Find the sum of all the numbers from 1 to 100. And Gauss later confessed to having recognized the pattern. All right, impressive, Gauss. Because there are 50 pairs of numbers, yeah, each adds up to... I knew that when I was 3, too. Pretty trivial stuff. Addition to the vertical column produces n terms, each of which is n plus 1. Okay, yeah. Pretty obvious stuff. Alright. He went on to a succession of triumphs, each new discovery falling on the heels of the previous one. The problem of constructing regular polygons with only Euclidean tools, that is to say with a ruler and a compass alone, has long been laid aside in the belief that the ancients had exhausted all the possible constructions. Gauss showed that the 17-sided regular polygon is also constructible. Damn. Crazy dude. Let's see. Advance in the area. Provided a rigorous proof of the fundamental theorem of algebra, which had been stated first by Girard. Okay, this is more history. This is cool, but this book is kind of repetitive IMO. Do you have a preferred number theory book? Okay, finally some math. Gauss introduces the concept of congruence and the notation that makes it such a powerful technique. He explains that he was induced to adopt the symbol hamburger, 3 bars, what do you call that, triple equals, because of the close analogy with algebraic equality. Yeah, okay. I guess it's transitive, reflexive, and associative. According to Gauss, the number of n measures the difference between two numbers, a and b. Then a and b are said to be congruent with respect to n, if not incongruent. Putting this into the form of the definition, n's a fixed positive integer. Two integers a and b are said to be congruent modulo n, symbolized by... You know, it's weird. I feel like I learned all of this in discrete math. This does seem rather redundant. Math curriculums are very strange, in my opinion. Yeah, I don't know. I've seen congruence before. Friendly introduction. Yeah, but I remember like taking a whole lot of time in my discrete math intro course to talk about congruence and like equivalence classes and stuff. I'm gonna go to the problems for now. Yeah, I guess discrete math, but discrete math and like intro to math is kind of, I don't know. You kind of cover a lot of the same concepts, at least at my school, right off the bat. All right, so let's go back to the problems. So problems 2.4. Okay, section 2.4. Number 2, number 5. I guess I should put that next to there. I'm just going to write down what actually is required in the homework and then copy it over. Can I just copy this? God, copying from PDFs is the worst. Number 2 and number 5. I'll leave that note there. What? The hint, but should direct you to 2.3. Okay. Okay, and then we got section 2.5, Diophantine equations, and section 2.6. So this stuff may be relevant, but it's basically a comment. All right, and that's enough. I don't need that preview for now. Wait, are you the Russian guy? Are you Vlad? Drawing tablet for math notes, I'm not exactly sure. I've seen a lot of people do it. The Discord link is broken on purpose. We're kind of, the Discord got too full. We're slowing down applications for the time being. Oh no. Do I really have to use the Euclidean algorithm? We have to do all 4 parts of this. Okay, this isn't actually that bad. B, C, D. Oops, god damn it. There we go. Okay, GCD 56 72 equals 56x plus 72y. This is all right. No, I've never competed at math. I don't know. I wrap text and it gets too long. live preview thing compile an actual HTML page? It does compile an actual HTML. You can do, yeah, the types compiler can render HTML on the fly. All right. Use Euclidean algorithm to obtain integers, satisfying the following. So you're basically looking for integers that make a linear combination of GCD 56 and 72. And forgot the dot at the end. What do you mean dot at the end? Oh, yeah, thanks. All right, I guess I'll write this out. Got 24, 138, 24x plus 138. I guess some people also just use plain parentheses for GCD. I think that's a little cursed though. I think that's like a tuple. It's interesting how like all different textbooks have different like notation for things. It's kind of annoying. Also, what's interesting is how like all different textbooks have different like names for different theorems. You know, it's like theorem 2.3. Like, can't we have a standardized name? Because now like I don't know. It's just annoying when they're like, oh, it's theorem 2.3 in your textbook. Can't we just like, can't that have like a unique ID that's the same across all textbooks so it doesn't like matter? Because then it's like just hella gatekept to that textbook. And like, yeah, the big theorems have that, like Euclid's lemma, but the little ones don't. Like the random corollaries and stuff, they should just be like all defined. I was thinking about like how you could represent everything as like a dependency tree, and you could do that in Lean, like yeah, for only the super important theorems. But there should just be a database that's like every theorem ever, and it should just have like some naming scheme that's like, I don't know, it's something like it's got like a path, you know. No, not theorem random number, but like it would have like a descriptive naming convention. Like it would be scoped by like what type of math it's used in, and then by like, I don't know, maybe you could scope it, and then there's like, you could call it lemma. There's like those different lemma, corollary, theorem, those different things, and then like you could just kind of describe in plain language how it works. But like if there was like a standard database, that would be interesting. Even if that would exist, math proofs wouldn't use it to gatekeep. Yeah, searching for random things in Lean is difficult. Yeah, that's what I'm saying. Like, if there was like a corpus of theorems, then if there was like a unique theorem ID generator that like programming, like they had like different scopes, and yeah, I think it's an interesting idea. Okay, the Euclidean algorithm for solving this stuff is basically that we can express, well, I don't know if I've ever used the Euclidean algorithm in the respect to get a linear combination. I'm just going to look for the there we go. Okay, GCD of two integers by listing all their positive divisors and choosing the largest one common to each, but this is cumbersome for large numbers. True, we hate doing that. A more efficient process involving repeated application of the division algorithm is the result of the 7 Book of the Elements. Has anyone ever read Elements? I've heard it's pretty banging. Although there is historical evidence that this method predates Euclid today, it is referred to as the Euclidean algorithm. Wait, predates Euclid? That's a jump scare. It's described as follows. Let a and b two integers whose greatest common divisor is desired. Alright, we have that. We've got 56 and 72. There's no harm in assuming that a greater than equal to b greater than 0. And then you apply a equals, okay. If it happens that R1 equals 0, then B divides A and GCD AB equals B. Otherwise, we proceed. The division process continues until some 0 remainder appears, say, at the n+1th stage. Alright, so basically we got 56 equals, well, I guess we should do the bigger one. 72 equals 56 times 1 plus 1416. All right, and R is not 0. It's not that math wasn't done before Euclid. He's the one that compiled it properly. I see. Okay. And then we're moving 56 over to be 16 times 3, 32, 48. Plus 12. That's not 0. Is this going right? Then we're moving 16 over to be 12 times 1 plus 4. 12 equals 4 times 3 plus 0. All right. What did that give us, though? Continues until some 0 remainder appears, say at the n+1 stage, where r to the n-1 is divided by r. 0 remainder occurs sooner or later because the decreasing sequence cannot contain more than b integers. The result of the following system of equations. So we have a big-ass system of equations. We argue that r sub n, the last non-zero remainder that appears in this manner, is equal to GCD AB. So 4. Yeah, I'd buy that. Bro, 56 is 48 plus 8. Generic looks maxer. Are you sure about that? 56 is 48. So you're saying I messed up here? No. That's correct. (16 times 3 is 48 plus 8. Okay. Okay. Whatever. And then we got 8 times 2 plus 0. All right. So the GCD, you could argue, of these two things is we argue that the last non-zero remainder that appears in this manner is equal to GCD, which means 8. 8 is the GCD of these bad boys. I swear there's always like some Germans or something that show up that's like, oh my god, this math is so easy. Yeah, there's always a bigger fish than you. All right. Yeah, this is not insanely hard math. All right, what are we actually looking for in this question, though? To find values of x and y that satisfy each of the following. To obtain integers x and y that satisfy each of the following, I mean, couldn't we say... We're basically trying to get those equal to 8. I'm confused on how they want me to use the division algorithm here to deduce these two values. Can we argue? I don't know, I guess we argue, okay. Our proof is based on the lemma below. GCD BR equals GCD AB. So the GCD is 16 and 8 is equal to the GCD of okay. Back substitute. Like what values? These values? Oh, let's go. I'm recognized by T. Soding. I never know how to say that guy's name. Euclid's algorithm, you have a load of equations, then go backwards through them. Oh. Yo. That's kind of interesting. I mean, you have 72 equals 56 plus 16, and 56 equals 16 times 3 plus 8. do the Euclid's algorithm, then you have a load of equations, then go backwards through them. I'm still not thinking about this in the correct way. I don't speak German, but yes, I think in German. All right. $56 equals 16 times 3 plus 8. I'm not sure like what substitution I'm supposed to make there. 8 equals 56 minus 16 times 3. Oh. 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 16 equals 72 minus 56. And then 8 equals 56 minus 72 minus 56 times 1 times 3. So I've been 16 equals 71 minus 50. 71? 72 minus 56. Technique here is to always leave your last remainder on the side of the equation. Equals 56 minus 16 times 3. Sure, 56 equals, or 8 equals. So we could say, I mean, that's the same as the GCD. Equals 56 minus 16 times 3. Eight equals 56 minus, and then 72 minus. And then we can, you're saying we can sub in for this 16, 72 minus 56. And is that, that's just weird to me. So this is 56 times 1. This is this of the form 72 times some y? Can you factor 72 out of it? That's what's confusing to me. now expressed as 16. And expanding the brackets, you have the solution. Oh, shit. Fire. Because then this is 56 minus, so then we'd get negative 4. 56. Or... no, we wouldn't, because we've got a 56. It would be negative 2. Hold on. I totally distributed that shit wrong. We have to distribute this negative 1. So we get a negative 72 plus. So there'd be a 3 there. 3 there. So then we'd get 4. We get something like that, right? And then just to verify, actually, could technically do this in Vim, but it's too late. Minus 3 times 72. Boom. Math major, by the way. Negative times negative equals positive. He's a math. That's awesome. This shit rocks. I can't believe that worked. Damn, that's cool. Oh my god. Wow. I could make this my career, low-key. Alrighty. Next up. I appreciate the people that don't roast me for my primitive math abilities. Alright. So you could kind of say that 138 is equal to 24 times... so 138 divided by 24, you could fit it in 4 or 5 times. That would give you 120, and then you get 18 left over. And then that could be expressed as 118 plus 6 oh, oops, that's wrong as hell. And yeah. And then 18 you could express as 6 times 3. Alright, now I'm not going to look at the chat and see if I can handle this by myself for sake of practice. And we get, so the GCD of these things is 6, is the, yeah, I would buy that. I think I could be persuaded. Yeah. Okay. So we got 24x. Now what's 24? But we did this last time by solving for the GCD. And we know the GCD is 6, so assuming that I didn't do... No, I don't know if I'll do it 4 times in a row. I'll save that for off camera because that's boring. All right, we got that equaling 6, and since we have 6 equals 6 is going to equal 24 minus 18. Times 1. And then what can we express 18 as but 138 minus 24 times 5? Times 5. And that 1 is nice because that's redundant. So then we're going to get a plus in there, and then we'll distribute that out. And we've got a negative, and then this will become a 6. Is that correct? Could someone verify it? Yes, let's go. You know, whenever I read a generic Looksmaxer, oh, what's up, Simon? I always think geriatric Looksmaxer. I think you're old as hell. All right. Now we got Oh, I only had to solve A and B. Wait, is that correct? Wow, I'm free. Sign issue? Sign issue. One of these is negative. Which one is it? How looks-maxed are you? Are you like the most attractive fella around? Alright, that sure ain't right. How about, well, that wouldn't do anything. Fuck. Yeah, so that is not correct by any stretch of the imagination. Sign issue earlier in the substitution. All right, I'm redoing this for practice. So 6 is equal to 24 minus 18. We can all agree. And what's 18 equal to? But 138 minus 24 times 5. Now let's distribute this negative. And we got something like this. Yeah, I distributed the 5 incorrectly. So what we'd get is something like this. I distributed it to all terms in there, which is dumb. That's got to be correct. Because that's going to be 120... 144. Yes. Okay, cool. Thanks for catching that. All right, boom. And I guess I don't have to do this. I'll just comment it in case I apparently do. Okay. Let's see what's up next. What do we got? Number 5, example 5. Oh, accidentally. Okay. For n greater than or equal to 1, show the following. love about types is you can just keep going on, yes, it is Zathra. You can just keep going, and like this will join lines automatically with the one above it. And positive integers A, B, show the following. I guess that needs to be capitalized. Damn. Okay. A. If GCD AB equals 1, then GCD A to the n, B to the n equals 1. Okay, that's interesting. And then they give us a hint, but I don't immediately want to look at the hint. So that makes sense because you couldn't take out extra copies of A and B, but how do you actually show that? Let's see. So trying to prove this, we're using this assumption, and then what are some facts about that that are necessarily true? So GCD AB equals 1 implies A times some x plus B times some y equals 1. If we had, for instance, all of that to the n, yeah, I guess A to the n, oops, B to the n. Well, does this necessarily follow? And does that help? Get some funny comments around here. So you're saying this is something I do instinctively. I see GCD and then I'm like, man, yeah, you can contact me by email. It's a free country. I can't reject emails, sadly. Yeah, I do this. Well, we have that implication. We also have the implication, like someone said, AN equals 1, and B times something. B times M equals 1. X and y in equation 2 need not be the same x and y in equation 1. So you could write a times a to the n minus 1 times x plus b times b to the n minus 1 y implies ap plus bq equals 1. Don't we have to go the other way with the implication though, or am I not correct? I'm doing problem 5. Did I just scroll to completely the wrong place? You're correct for me too. GCD. Oh, contrapositive. That's smart. Contraposition. We say some p divides a to the n and b to the n, then it divides both a and b. Contradiction. Okay, so you're saying we will show contrapositive, which would be that does not equal 1. A to the n. I like that. A to the n. You know, actually, I'm going to record a macro because I keep having to do this. I'm going to call it n. Q, n. We're going to say a, n, escape, q. Okay, a to the n plus b at n. Actually, that's just harder than typing to the, never mind. Does not equal 1. Implies GCDAB does not equal 1. Correct? That's the contrapositive. Say some p divides and then it divides a and b. Contradiction. Well, yeah, some p greater than equal to 1 is the same. Is the same thing, essentially. So p greater than 1 this should not be a plus. B to the n equals p. Primes are always greater than 1. Okay, that's not necessary, I guess. Oh man, I love the AI doom. Occasionally, why do you even bother? Yeah. We're all wondering that deep down. I have to spread the hate. Shit, yeah, I'm gonna give up and maybe I'm just gonna be a ski bum. But yeah, that just makes it easier because for primes, p divides a to the n implies p divides a. So you're saying we'll show the contrapositive equals p is simpler. Okay, fair enough. And then we have that GCD. I'm going to copy this. I'm not trying to type all this out. we have that implies that, oh, I should have copied the equals p. That implies that a to the n, p divides, and p divides b to the n, which implies p divides a and p divides b. So isn't that like the completed proof? GCD doesn't necessarily equal a prime, but a prime divides it. Why does the last implication hold? Oh, we say GCD is greater than 1, then by fundamental arithmetic. Show the contrapositive. Instead of equals p. So I guess I'm missing this step, just for clarity. We'll say it's greater than 1. P divides okay. And but a p dividing that implies that p divides each of the things in turn, and that implies, because if a prime p divides like a to the 3, that means it divides a, because we can't introduce extra factors like that. Oh, this is off screen as hell. That doesn't make any sense. So that makes sense. That I get why that holds. If you assume the fundamental theorem of arithmetic, you can just say that a and b share no prime factors, so neither do a to the n or b to the n. But it's the next chapter in the book, so a bit unkosher. Oh, does it say not to use fundamental theorem of arithmetic? Rookley YT. Mech vibes. Line 72. Oops. God damn it, Zathra, and your macOS scroll bar problems. Where does it say that? Line 72. Oh, shit. God damn it. Should not use the fundamental theorem of arithmetic. With a hint for 5. Directs you to 2.220. All right, so this is bogus as hell. Oh no. So no fundamental theorem of arithmetic allowed. C problem 20A section 2.2. Should we look at that? I wish there was a better way to search in PDFs. I don't actually see that 20A. Problem 20A in section 2.2. Is my PDF cut off? That's 2.3. Yeah, I only see up to 11. Section 2.3. Oh shit. Man, thanks for thanks for actually reading stuff. Directs you to 220, but it is directed to 2. Jeez, I need to read the directions, use the given. I had a math teacher that always said that. Okay. GCD AB equals 1, then GCD AC equals 1, then GCD ABC equals 1. Hint, because 1 equals AX plus BY equals AU plus CV. For some XY UV, 1 equals AX plus BY times AU. And we can do that because they're both 1. And then we can take an A what? What's this monstrosity? This is the result of distributing. What the fuck? Oh, okay. Yeah, I buy that. Induction. Math major, by the way. You wrote A as a linear combination of A. You wrote A as a linear combination of A. What a cursed sentence. And BC, and it's 1. Wait, what? N is greater than or equal to 1. GCD A to the N, B to the N equals C implies A to the NK plus B to the NQ equals C, in particular for N equals 1, as AK plus BQ equals C. Oh, man. We got Johnny willing to help in an hour or so too, which is cool. Obviously, asks you to prove it for n is greater than 1. Yep. So induction proof. Proceed by induction on n. Base case n equals 1. That's trivially true. I'm not even gonna trivially true. Okay. Induction. Step. Assume GCD. Well, we want to assume this whole statement. What's interesting is I see sometimes in induction, some people like will use n minus 1 to prove n rather than n to prove n plus 1. From GCD a equals b equals 1, try to show GCD a b to the n. What? I want to be an unemployed homeless bum. That's my career direction. Okay. So we're assuming that implication, correct? And then we want to show that because this is the case to the 1. Or I guess we could also do this. N minus 1. Okay, this is gonna get annoying though, so I think I'm gonna bust out actual paper. This is lopsided AF. I just have my phone propped on top of ski poles. Okay, please don't fall. All right. All right. Oh, yeah. I guess this is at such a horrible angle. Is this remediable? Maybe I can rotate it in software. Here we go. Shit. There we go. That probably won't fall. Problem with ski poles is they're like rollers. Like this thing really does not want to stay on them. Nothing brings me joy like having a low quality streaming experience. Alrighty. I'm just not gonna move. My phone doesn't have a case on it either. Alright, don't breathe. Yeah, does GCD AB equals 1 imply that GCD AB equals A squared B squared equals 2 or equals 1? Yeah. If it works, then don't touch it. I don't know if it does work. It's slightly lopsided. So, is this bad boy true? Is the real question. Oh, just do GCD A B squared first. So that wasn't a typo. Is that true? X plus by equals 1. And what we're trying to show is ax 1 plus b y b squared y1. But you won't prove it if the power is a power of 2. It's that theorem in the book. Oh, the hint they gave? Like the GCD AC GCD AB equals 1 and GCD AB equals 1. That's the same thing twice. Implies GCD AB squared equals 1. Oh. Oh. Shit. Yeah, I do not see that kind of stuff easily. That makes a lot of sense, yeah. Since GCD, like A, B, let me actually go to that theorem. GCD AB equals 1 and GCD AC equals 1, then GCD wow, yeah. So Yeah, I see that, I suppose. That does make sense. Could you now extend GCD a to the bn equals 1 for any n? I mean, yeah, couldn't you just like say that you're just like adding the n's and the exponent, like, and those are the two factors, like if that makes sense, because if ax plus by and ax plus by I mean, you set in the theorem b equals c. So you could have like b to the n minus 1 times b. And then, like, would that work inductively? I see. Gotcha. But to do that for both terms, you just do the same thing for a times a to the n minus 1. Write out the theorem, say c equals b to the n, or c equals b to the n minus 1. It's b to the n minus 1. And you're talking about the hint theorem that if we have GCD because we're trying to get n to show n plus 1 or n minus 1 to show n, if for an inductive proof. So like GCD a to the n b to the n equals GCD AC is this a strong inductive proof? Equals GCD AC I don't know why I crossed it out. C is b to the n minus 1. And then that implies, or that also equals GCD A B C where C is b to the n minus 1. GCD AB equals 1, and GCD AB to the n equals 1 implies GCD A all right. So first showing GCD AB equals 1 equals GCD A to the B n. Interesting guy, Rookley. And we want to show that implies GCD A CB or B to the n times B. That was the hint theorem in the book. Oh, you think I should prove the full hint theorem? I was just like thinking of taking it as a given, but I guess you're right. Just for the sake of my understanding. So that's what I will prove in a minute. But GCD AB equals 1. GCD AC equals 1 implies GCD ABC equals 1. Okay. AX plus BY is 1. AU plus CV equals 1. And then they said that multiplying these together, AX plus BY times AU plus CV would give you this nasty polynomial expansion, AUX plus CVX plus BCYV, which, because we've got an A times some term and then a BC times some term, and this is all equaling 1, shows that the GCD ABC equals 1. Yeah. Yeah, okay. I buy that. Um, so the proof follows basically the exact same structure for proving this here, which is that we have ax plus by equals av plus b to the n times u, and that all equals 1. Since these are both 1, we also have ax plus by times av plus b to the n u. And then this could be expanded. Ax times au plus ax times b to the n. Oh, that's a v, not a u. Shit. Why do people always pick those variables? And then we've got a by times au, or av, plus a b to the n u times by. Let me see if I can zoom in a bit on this. This is what we get all the way to the edge here. There's no great way to zoom on OBS that I know of. All right, and then we're looking for essentially a linear combination of A, which we can get decently easily, which is going to be A times x av plus x b to the n. Well, the b to the n should ideally be kind of separated, I think. Because we want b to the n times b. In that example, oh, they have a c in there, it's fine. There's a times that nastiness plus by times v, and then so that's an a all gone out of that, plus b to the n b times uy. And that's sufficient argument that we can just say that's like an m, and that's a z, So AM plus which implies the GCD of A and B to the n equals 1, or GCD A B to the n plus 1 equals 1. And then, yeah, by symmetry, you could do the same thing. Yes, perfect, but we knew that from our theorem. True. Note the result on the right is more general. Like in this particular question, we shouldn't have to do any algebra. How do you mean we shouldn't have to do any algebra? Oh. X times a to the n plus y times b to the n equals 1 can be written as a times x to the n minus 1 plus b times oh, what's up, Raj Jr.? The number theory is going pretty well. Cupcake makes an interesting argument. I finished calculus, my guy. That was ages ago. I guess analysis is technically extension of calculus. All right, to complete this proof. Thanks for the $2, man. I appreciate it. Okay. GCD AB equals 1 implies GCD A B to the n equals 1 for all n. Proof by induction. Claim 2. GCD AB equals 1 implies GCD A to the n b to the n equals 1 for all n. Use claim 1 and symmetry of GCD. Wait, I'm confused though that So you're saying, Padergill, that we don't actually need proof by induction here. At all. We can just show p to the n implies, or p to the 1, a to the 1 implies a to the n, and then we're good. Oh, what's up, Johnny? How's it going? Yeah, we covered the basics of primes. We're not allowed to use we're not allowed to use fundamental theorem arithmetic, though. Unfortunately, that's hence the convoluted nature of this approach. We do need induction, but using algebra was not required. Yes, primes are not allowed. Yeah. Oh wait, hold on. Someone's calling me. I'm gonna have to end stream. I'll probably be back.